Hello everyone, welcome to a fresh new lecture on the topic Coherence Analysis for the part of the course on signal processing algorithms and architectures. This is Dr. Anirban Dasgupta and let's get started. So, we will recap something from the module 1 time domain signal processing where we differentiated power and energy signals. So, we defined signal energy as sum of the squared values of the signal from negative infinity to positive infinity. And if this energy is finite, the signal is called an energy signal. So, aperiodic signals of finite length are typically energy signals, like this is an example. Similarly, for periodic signals of infinite duration, we do not define the energy because that will be infinite. So, we define something called the power. The power is defined by this relation, where this is the energy thing, but here we are computing over a value n, and then what we are doing is we are using this limit. So, if we see that the power is finite, then the signal is called a power signal. And say a sine wave. So, this is just a part of the sine wave, this is extending to infinity and also starting from negative infinity. So, this is a power signal. So, power of an energy signal is 0 and the energy of a power signal is infinite. Now, we will introduce a new term which is energy spectral density. So, energy spectral density is how the energy of a signal is distributed across the different frequency components. So, how do we obtain? So, let us say we have an analog signal x of t. Of course, this is for the theory, I am taking this analog signal. For computation purpose, we will again go back to the discrete time counterparts. So, this is a graph where your psi xsf is your energy spectral density and this is computed in this manner. So, this is kind of from the Parseval's theorem that your energy in the time and frequency conservation. So, I will take the Fourier of the signal and square it, and why I do from the Fourier, because I want to get for each frequency component. So, power signals have infinite energy as already discussed. So, the Fourier transform and your energy spectral density may not exist for a power signal. May exist also, but the problem is that how do we get such kind of information? So, for this we need some alternate spectral density definition with similar properties such as the energy spectral density, and here comes power spectral density to the rescue. So, power spectral density describes that how the power of the signal is distributed across the different frequencies. So, if you have a signal x of t, the PSD is usually estimated using different methods, like one method is periodogram or the Welch method. We already discussed the FFT based PSD estimation. So, how do we define the PSD? So, the PSD is defined by the formula Pxx of f is a limit t tends to infinity 1 by t expectation. Now, why this expectation operator is used? Now, typically this will encounter for stochastic signals as well. If the signal is deterministic, that realization is the same as the expected realization, but if the signal is stochastic, there can be several realization. So, we take the expectation, and typically what happens is, so like I said that power spectral is for periodic signal or a power signal, and practically you cannot capture the entire power signal because it goes from negative infinity to positive infinity, and we do not know what is negative infinity and positive infinity. So, technically we will take a time limited version, and hence because of windowing and other factors we get a noisy spectra. So, this is typically corrected or estimated using this Welch's method. And what is this power spectral density related to the signal? It is the Fourier transform of the autocorrelation function. So, you can find the autocorrelation function, which we have already discussed in the time domain. You take the Fourier transform, what do you get is the power spectral density. And autocorrelation again, so for a stochastic signal you can get it using the formula expectation of x of t and t plus tau, where tau is giving the lag between the 2 points in the signal in time domain. Well, this is an example of a power spectral density which says that these are the dominant frequencies present, or these frequencies have very high power, others are kind of having no component or no power, and this is usually obtained using the Welch method. So, that is why we get a clean smooth estimate of the PSD, and this PSD is also useful in finding the dominant frequencies in the signal, and that is the frequency estimation problem. So, well, like correlation had two forms in the time domain, autocorrelation and cross correlation. Here also we have the auto power spectral density and cross power spectral density. So, autocorrelation, if you see, this is synonymous to the not synonymous, but the analogous part of the APSD, and this is representing that how the signal is distributed across different frequency component, right. What about the cross power spectral density? Now, here what we are doing, like in autocorrelation, we are doing the power for the same signal multiplied twice, but in the cross we are using two signals and one signal we are finally conjugating. So, now we will come to the term coherence. So, coherence is a measure of correlation between two signals x t and y t in the frequency domain. So, this is kind of a normalized version of the cross power spectral density between two signals. Like we had a normalized version of Pearson correlation coefficient in the time domain, similarly coherence is kind of analogous to this concept. So, this is the formula to calculate the coherence. So, C of x y f is the ratio of the square of cross power spectral density divided by the product of the auto power spectral density of signal x and signal y. So, this value will be between the range 0 and 1, where 1 indicates high coherence and 0 indicates low coherence. Let us see an example. So, if we have a sine of frequency 40 hertz and another sine of frequency 50 hertz. So, if we see the power spectral density, so Pxxf will have a peak at 40 and Pyyf will have a peak at 50. But if we see the cross power spectral density, no frequency components are common, so the coherence will be 0. So, this is an indication that how my common frequencies are linearly related to each other. So, this is what I just showed or told in the previous example. So, we have a sine wave, and of course, this is a windowed version of a sine wave, not the you cannot technically have the full sine wave. So, this is a 40 hertz sine wave and this is the 50 hertz sine wave, and this is the cross correlation. So, this is in the time domain. So, what happens in the frequency domain, the cross coherence, and ideally you should get a value which is nearly 0, but because of this windowing effect you see that there are small fluctuations in the frequency spectrum or the coherence spectrum. So, what is the intuition and meaning of coherence? So, this is essentially a frequency domain correlation, and it will show that how the phase and amplitude of two signals are related at different frequencies. So, in correlation we see that how they are related in time, this is a relation in frequencies. So, if you have a high coherence at certain frequency, that indicates that at this frequency there is a strong linear relationship between the two signals, and which technically means that one signal can be predicted from the other signal at that specific frequency. On the other hand, low or zero coherence at a specific frequency means that the signals are uncorrelated at that frequency, or changes in one signal are not linearly related to the changes in the other signal at that specific frequency. So, if it is a high coherence, like for example, say we are recording brain signals, and say we have recorded brain waves or EEG signals from two regions, say from this region and this region, and say we are interested in a specific band, say alpha band, which is typically 8 to 12 hertz. Now, those who are into EEG processing might appreciate this factor, otherwise understand that alpha band is a specific frequency band in this frequency range in the EEG. And if there is a high coherence between two regions, like say the frontal region and say the back of the region, like occipital region, so that means there is a functional connectivity between those regions. Low coherence, where is it useful? So, suppose we have in a communication system, we have a low coherence between the transmitted and the received signal, then it can be an indication that there is noise or interference, and that has affected certain frequency ranges. So, there are several applications of coherence like correlation. So, in neuroscience, one example just I gave, where you can see the different brain region and see for which activity, like if you are watching a movie and watching a lecture, will the brain react similarly? So, these coherence can give you a lot of indication regarding this. Or if you are thinking and if you are meditating and if you are focusing or concentrating in someone, how the coherence between the different signals will tell about the mental state. Then vibration analysis and structural health monitoring, coherence is often used in mechanical system. So, as I said, this low coherence might indicate that there are some noise in the input and output, or the input and output is affected. If the input and output has low coherence, that means there is some nonlinearity and noise which is introduced in the system. Now, how do we estimate? Like as I said, this APSD and CPSD, these are power spectral densities, and because of this windowing, and also we have lot of noise in practical scenarios. So, direct calculation using the method which I said may give you a very noisy estimate. So, what Welch method suggests is that it will divide the signal into overlapping segments, and then you apply a window function to reduce the spectral leakage, and this window may not be a rectangular window, you can have different forms of windows, and then the periodograms will be averaged across the windows. So, this will result in a smoother and more reliable estimate of the PSD. This is one example. See, this is an estimate of PSD, which is a standard periodogram, and say this is denoting two dominant frequencies somewhere like 50 and 150, but there are noisy components which does not really mean anything but noise. So, Welch method we get a smoother estimate of the PSD. So, you are not sure here whether this is a noise or this is really some frequencies are present here, is very confusing, but Welch method will average them out and you get a smoother estimate. So, this is the algorithm to compute the coherence. So, we start with two discrete time sequence, and now we are back to the discrete time domain, and then we will use the Welch's method. So, first we will estimate the Pxx and Pyy just as mentioned earlier, but this will be using the Welch method to get a smoother variant. So, we will use the Fourier transform also and the Welch method also to compute the APSD. And similarly, we will calculate the CPSD as well by taking the cross spectral density, and this is the final formula to obtain the coherence. But practically, what are the main things for which coherence analysis is challenging, and there is still research going on to get a very good estimate. So, one is windowing and spectral leakage. So, what is spectral leakage? Spectral leakage, like to explain in a nutshell. So, say if I have a sine, and when I say sine, I mean minus infinity to plus infinity, I should get a spectra at, say if this is a 50 hertz sine, I should get a spectra at 50 and minus 50. I say just seeing the positive half, so I should get a peak at 50. But in real estimate in our digital hardware, we get a lobe like this around 50, which means that the peak which should be only at 50 is spread out around this region of 50. And why this happens? So, this is called windowing effect. But why this specific spread happens? This happens because, so we are taking a window of this, window means a small region of this sine wave, not the full sine wave. So, if the sine wave is x of t, this window is basically multiplying with a rectangular function which is having 1 within this range and 0 outside. So, technically we are multiplying x of t with r of t, which is the window function, rectangular window, and this estimate is the Fourier transform or the spectra of the combined signal or the multi-product of xt and rt. Now, when we have multiplication in the time domain, we should have convolution in the frequency domain. So, x of omega is convolved with my r of omega, and x of omega is this one, which is only one peak at 50 or maybe two peak at 50 at minus 50. And what is r of omega? R of omega is the Fourier transform of this rectangular window, which is kind of a sinc nature. So, this is the Fourier transform amplitude. So, magnitude spectra will be something like this. So, if you convolve this with this, you should be getting something like this. So, to minimize this, instead of rectangular window, better windows are there like the Hamming window and the Hanning window, and these are applied to segments of the data. But this is also a trade off, that how will you have a good frequency resolution and what size of window you should select. Then averaging and smoothing, like as I said that this Welch method is smoothing out noise, but it may also smooth out some frequency information. Say there is a fault and that fault has a small frequency component, but Welch method can totally remove that. So, this is again a big challenge, that which window or how much you should smooth, this is a real challenge. Then length of data and frequency resolution is also a challenge or practical consideration which you should keep in mind, that should I take a very long data or a very short data, and also if I have longer data, so I will have a finer frequency resolution, but you might be required to do lot of computation to get stable estimates. And in multivariate systems, like say in multi-channel EEG, so I gave example of only 2 channels, but there can be many channels. So, in such a case, how do you basically find the coherence? So, in such cases, partial coherence is also observed, that will give you the linear relationship between 2 signals while accounting for the influence of other signals. It is very much synonymous to the concept of this mutual inductance, like where you have lot of circuits and mutually how each other will influence the inductance. Lot of inductors are there in the circuit. So, this is again very much analogous to the analysis of superposition, where you remove all components and keep 2 kind of a thing. So, you can remove all effects of other signals and then you can calculate the coherence. So, that is all for this lecture. Thank you all. We will meet again.